Very good morning, or good early morning to some. We shall go through the processes of sharing screen, making sure to select share sound, and hopefully getting the right screen.
Looking good.
Yes. Rather stupidly, I've not, after all this time, I've not got my monitor screen up. So relying on you, Paul, if things go wrong.
Yep, it's good.
Okay, good. And we go to full screen. That should be. Okay.
Yes.
Right, off we go. Right, so the title of the workshop is Spectrum Lab and its uses. I'm afraid that's a bit of a misnomer because Spectrum Lab is a very flexible application, and if we were going to cover all of its uses, we're going to be here for some time. So I also apologise up front in that some of the bits that I've done really assume the viewer is an absolute beginner. So most people, I hope you'll bear through that with me and understand why. Okay, the agenda, I split it into 3 parts. First bit about Spectrum Lab, and I'm going to say a little bit about Fourier Transform because it really underpins Spectrum Lab, and it also is not a perfect animal. So it is useful to understand the pitfalls when working with something that is so reliant on the fast Fourier transform. Part 2 is the main part, functionality, and then part 3 I go through a couple of applications where I've really learned the little that I know about Spectrum Lab as part of getting started on those applications. I reckon part 1 is about half an hour. I reckon part 3 is about half an hour. I reckon part 2 is an hour or so. So obviously we'll have breaks for questions. I suggest the first break for questions will be at the end of part 1. If this slot sums to 2 hours, that gives us an hour for me having drinks in particular, but to allow others to have a break. Right, let's get started then. Okay, so what is Spectrum Lab? Well, basically, it's an application developed by Wolfgang Beuscher, a German radio amateur, DL4YHF. And originally it was developed for amateur radio applications when the first digital formats were being developed. It runs on Windows, and I understand it runs on Linux under Wine, but I've never tried that. It's not open software, but it is very free software. Wolfgang doesn't even ask for donations. It's for such a powerful animal, it's quite a deal. Other people have contributed. Some of these are statutory acknowledgements, but Paul Nicholson, for instance, has done a lot of work at VLF and ULF, ultra low frequencies, Marcus Vester, and work by the various members of the Radio Society of Great Britain low frequency group. So people have contributed because they can see the value of the bigger picture. Okay, what is it? Well, it's a flexible analysis and development tool, and to complement that flexibility, it has a built-in scripting functions with a command interpreter, so you can tell it what you want to do and get it analyzed, etc. There's also a built-in HTTP server, which I understand is sufficient to allow it to stream to the web, but it also means that it can support the control of other applications, and indeed other applications can control Spectrum Lab. There is a remote interface there. What does it do? Well, I mentioned about the amateur radio stuff. Natural radio, so this is coming down to VLF and looking at the interaction of lightning strikes with the ionosphere and the Earth's magnetic field to produce some quite eerie effects, whistlers and spherics and whatever. Other VLF applications, such as sudden ionospheric disturbances, and we'll cover one of those at the end. Meteor scatter, another one I'm going to talk about at the end, and also other meteor-related radio applications. Audio amplifier testing, animal voices, so that's translating sound that is outside of the range of human hearing back into audibility. And I don't know if people remember, but a few years back, tragically, a Malaysian airliner disappeared into the, I think it was the South Pacific, and was never found. But looking at the news reports of the search for the black boxes, lo and behold, there was the Australian Navy using Spectrum Lab to try and detect the audio beacon that's incorporated in these black boxes. So a very wide range of applications. And really the secret is in the name. If you look up lab in the Oxford Dictionary, it says it's a room equipped for scientific experiments and research. Well, here the room is the sound card. The computer sound card, whereas the equipment to do those measurements are the various software tools that or software-based tools that are incorporated in Spectrum Lab. So really simple graphic, as I mentioned earlier. Basically, take your computer. In the good old days, there actually used to be a separate piece of circuit board to handle the sound. So computer sound card was relevant. Nowadays, it's all incorporated on the motherboard, but the name sticks. And also you can have external sound cards connected through USB and the like. And Spectrum Lab sits on top of that. So in the computer sound card, you've got the analog to digital converter on the here, which converts your analog signals through to digital. And at the other end, the digital to analog converter, which takes the digital and converts it back to sound. Spectrum Lab sits on top of that. It interacts with your monitor and keyboard and hard disk to allow you to control things. It also provides a couple of extra functions in terms of taking additional inputs. And as I say, there's the HTTP server. Onward. We've talked a lot about sound cards, but it's not just about sound. So it works with electrical signals coming from any analog source. No, so not just a microphone. You can have a loop antenna, a radio receiver, any instrument that provides an analog output in the frequency range that is handleable by the sound card is suitable for work with Spectrum Lab. The other part of the name is spectrum, and back to the Oxford Dictionary, which defines that as a range of waves, light waves or radio waves. But actually, we're looking at the frequency domain as opposed to the time domain. Your traditional oscilloscope is in the time domain. This is something different. And we're now going to try the first of a restricted number of videos. I was hoping to do most of this by video, but unfortunately Zoom just cannot handle the cursor and the amount of detail on the screen. So I hope this works.
Here we have 4 screens from Spectrum Lab. In the bottom left, we have the component screen showing the various blocks of functionality within Spectrum Lab. You can see that I've got the signal generator here switched on, and that's controlled by this panel here. I've also got the input monitor switched on, and that's the output of that is being shown here. And finally, I've got the spectrum analyzer switched on, and the output of that is shown here. Both the input monitor and the spectrum analyzer are connected to point L1, which is here, and effectively the output of the signal generator. So what we're seeing at the top here is two representations of exactly the same signal. In the left screen, we're seeing the variation of energy in the signal with time along the x-axis. This is the time domain. In the right screen, we're showing the variation of energy in the signal with frequency. It's frequency along the x-axis. This is the frequency domain. So as I say, two representations of exactly the same signal. Right, whilst I'm here, I might as well just do a little demonstration of the functionality we've got. If I come down to the signal generator control screen, I can control the frequencies of the three signals using these slider controls here. Sort of like that. Whoops, that's right on the same. Yeah, okay, take it a bit like that. And I can change the frequency of this one down here. And you can see the variation in waveform there that's happening. These controls here give me the ability to increase or decrease the level. So I will increase the level here. And I can go up to the point at which I start to overload the system. And Spectrum Lab is showing me that something is not quite right. So I'll bring this level of the signal down here. So finally, I'll just switch off one signal. I'll switch off the second signal. And so now we have a pure sine wave here and a single frequency here.
So that seemed to work. So having established that we're working in the frequency domain, how do we get there? Well, the traditional way was a purpose-built piece of equipment. This is an example of a spectrum analyzer for radio frequency stuff. Weighed or still weighs 40 kilograms and used to cost about £40,000. The price or the weight has come down in the modern world, but they're still expensive beasts. But they do tell they do give the right story. They are precision instruments. The other way is to use the digital signal, first digitize the analog signal and use a mathematical technique called the Fourier Transform. As I've explained before, if we're digitizing the signal, we take regular samples, we measure them, and really this process is the basis of our life today because everything, audio, video, it's all digital. Except from where it comes out the camera, or rather the process in the camera or the instrument or your voice, and it stays digital until it needs to come back to your eyeball or eardrum. So this is an absolute fundamental part of our lives. The golden rule, which you'll get absolutely fed up of me mentioning as we go through, is that if this is going to work, you must sample, measure the analog signal at least twice the highest frequency in the signal. Right, okay. So just a bit of background. The name comes from Joseph Fourier, a French mathematician and physicist. There was another French Fourier living at the same time. He was, oh yeah, forget that. Anyway, okay. But he came up with the concept that any function of a variable can be expanded as the series of sine waves. So you can take a very complex signal and you can split it up into a series of very simple sine waves. The process of doing that is called the Fourier Transform. The end result of doing a Fourier Transform is, believe it or not, a Fourier Transform. So you get a Fourier Transform from a Fourier Transform. It's all very simple. An interesting point is that the Fourier transform, the principle applies to spatial functions as well as time-varying ones. We're going to be talking time-varying stuff here, but the same principle applies to an image. You can take an image and split that down into a number of simple functions. And if you've got those simple functions, you can then recombine them to get back to the original image. And of course, this is the basis of aperture synthesis telescopes that are used in radio astronomy. Right, so the basic principle is that you take an analog signal, you sample it and convert those samples into values, and then you feed blocks of these samples, not individual samples, blocks of samples, typically thousands of them, into the FFT algorithm. And out pops another block of values, but this time those values describe the amount of energy in different frequency bins. So you can use those that block of information to get your spectrum of the signal. The important thing to note is that the values that pop out here are derived from all of the samples that go into the FFT. So every single value that comes out of here is a function of the, say, 8,000 values that go into here. This is the equation. I'm not going to go into it because I'm no mathematician. But the crucial thing about it is this symbol here, which stands for the sum of. So it's derived, the Fourier transform is derived from a huge number of calculations. The task is so difficult that it's for a long, long time, it was really just a mathematical nicety rather than having any practical application. And the computation time is proportional to n squared. So if we've got 8,000 samples going into the FFT, you can understand the large numbers that are involved in these calculations. But in 1965, John Tukey and James Cooley rediscovered an easier way, a faster way to compute the Fourier transform. And this is called the fast Fourier transform. And the computation time is proportional to n rather than n squared. So if we're talking about tens of thousands or even hundreds of thousands of samples, you can understand the difference. Interestingly enough, it is a question of rediscovered. Carl Gauss had the principle of the fast Fourier transform in 1805, but never got around to actually publishing it. Okay, so very useful mathematical algorithm, but it has its limitations. I've mentioned one already about the highest frequency driving the sampling rate. Two other important things is that the FFT calculation is only valid when the block of samples contains an integer number of cycles, which is easy to do if you've got a constant tone, but we want to use this with signals that contain lots of different frequencies. And secondly, the signal must remain constant within the time covered by that block of samples. And that's a finite time, and it can be a long time. So these really make it impractical, in its purest sense, for realistic signals in practical signals. And what happens is that the FFT generates false components, something called spectral bleeding. This is an example of how the FFT can lead you up the garden path if you're not careful. This is the reflection of a meteor event. We have the quickly descending frequency. This is frequency in the y-axis as the meteor decelerates, as it burns up, ablates in the atmosphere. So rapidly dropping frequency. And then we've got the plasma trail that's left that is moving substantially slower than the original meteor, and therefore is sort of static in frequency. But these spikes are purely invented by the FFT. They're nothing at all to do with the input signal. The reason they're generated is that we're using this is from using the Graves space radar to illuminate the plasma trail, and that radar switches direction every 0.8 seconds. So you get terrific discontinuities in the signal going into the FFT at 0.8 seconds. Right, and then another limitation which I've alluded to is the relationship between time and frequency resolution. Frequency resolution is driven by the number of samples you use. So if you want to look at more detail of the spectrum, then you just feed in more samples to the FFT. But it takes time to collect those samples. These samples come into the system one after the other. So you've got to wait until you've got enough samples before you can set the FFT going. So better frequency resolution is a penalty, is poorer time resolution. And this is just some figures illustrating that. So if you have 4,000 samples going into the FFT, you get a bin width of just under 3 Hertz. So the output shows the energy in bins of 3 Hertz width. And it takes just under 1/3 of a second at the sampling rate that I'm using here to collect those samples. If you jump up to 16,000 samples into the FFT, wow, now your bin width has dropped to only 0.7 Hertz. But the penalty is it takes you 1.36 seconds to collect those samples. So the output of the FFT for each frequency bin will be based on 1.36 seconds worth of samples. Okay, so we do have mechanisms of trying to work within these limitations. The first one is easy. You just sample at a high enough rate to avoid this sort of fallback concept if you don't sample fast enough. I think I might have skipped over that. Fallback is the name of what happens when you feed frequencies higher than twice the sampling rate into the algorithm. What happens is that the higher frequencies are folded back into the output of the FFT, so causing problems. So anyway, to come back, what we can do to improve the spectral bleeding thing is use something called a window function. If this is our input signal, what we do is we apply a window function to it. And what that does is it reduces the value of the samples at the start and end of the block. So we get this. Before it goes into the FFT. Effectively, this means the FFT sees blocks of samples of identical value at the transition point, and that improves the appearance of the output. But this has a really significant effect on impulsive events like meteors or lightning, things that happen very quickly, because if this block of samples is over a second, then it's quite possible for that impulsive event to happen at this point, in which case it'll be suppressed by the window function and give a lower value. So that's an issue. This is an example of that issue. You won't be able to see the detail, I think, but what we're looking at here is 4 instances of Spectrum Lab running on the same computer. You can run multiple instances of Spectrum Lab at the same time, and in fact, there is one individual who runs no less than 21 instances of Spectrum Lab on his computer simultaneously. You're only limited by your resources inside the computer, the CPU or memory, that sort of thing. So that does show just how useful the Spectrum Lab can be. But anyway, what we're looking at is the timestamps from these 4 instances from meteor events. They're all fed from the same source, from the same receiver. So you would expect that you'd get identical results, but you don't. The various instances are missing some of these events. And the reason for that is the effect of the window function. Looking at longer time scales, this is the plot with number of meteor events per 10 minutes taken by 4 instances of Spectrum Lab running from the same input. And you can see the variation here. This should be, if we can't get our own computer to give consistent results, how are we going to compare data with other observers? By using the window function, step back. We're coming on to another concept now. This is the window overlap. We just talked about the window function. This is the window overlap. And as the name suggests, what you do is you overlap FFT calculations. So you use samples in each FFT calculation that were also used in previous ones. If you come to this middle point, so if you have a 75% overlap, only 25% of the values going into the calculation are new ones. The others have been used in previous FFT calculations. So they're overlapping. That means you can get a much faster FFT rate, and with 75% overlap, if you do if you look at things, you'll find that a meteor or lightning event will fall within the peak sensitivity of one of those FFT calculations. But if you want to do precision stuff, then you've got to look at something like 87.5% overlap, where each FFT only contains 2.5% new values. And this, of course, is very demanding on the system and the processing capability. But the results show that it does work. And this is the same setup now with 75% overlap. I did some sums here, or ran some different simulations, and with the 87.5% overlap, I got 368 events. And then as you decrease the overlap, you get correspondingly more lost events. So that demonstrates the principle. So summarizing, before we have a break, I haven't been looking at the chat facility. In fact, I'm not quite sure when I can see it, but perhaps Paul can provide some feedback on questions or whatever. So summarizing, the fast Fourier transform, it's computationally efficient and low cost in today's world. But it can only provide an approximation with dealing with real life signals. We talked about the window function that improves that approximation, but at the expense of problems with impulsive events. And by using window overlap and a higher FFT rate, then you can improve the situation. So I wonder if there are any questions.
I've got one, Paul. Is Spectrum Lab able to take advantage of the GPUs in these modern cards, like the NVIDIA GPU stuff?
I believe not. Spectrum Lab goes back a long, long way. The first system was done under DOS, and it's been gradually evolving since then. But as I say, this is free software. Wolfgang Beuscher has a day job, so this is virtually a labor of love, except that he gets lots of love back for it. So if he started again, I'm sure that would be the case.
It's maybe something that he could add. I mean, they're becoming very prolific, and of course they have immense computational capability, which is exactly what you need for this sort of number crunching.
So do we have any more questions? So I'll move on to the next part of the agenda, which is where we're going to go into Spectrum Lab and look at some of the processing to begin with. Then I'll cover the actions where you control the setup, and finally we'll have a look at how you configure Spectrum Lab. Okay, so this is the block diagram of the Spectrum Lab, showing the various processes and tools available. Basically, the center bit is two signal chains, hardly surprising as it's based around a sound card, and hardly surprising, one chain is called the left channel and the other is called the right channel. You can see the number of blocks and paths that are included in the signal chain with switches to be able to route signals around it. Around that basic signal processing path, we have a number of instruments to monitor and analyze what's going on, counter there. We have a time domain scope, an oscilloscope to be able to look at the signal. We have a sound recorder, we have a signal generator, and we have a number of other processes. We have a number of points in the signal path that are labeled L1 to L6, well actually L0 to L6, R0 to R6, and we can connect these instruments to any one of those points. So to look at the functionality, first of all, I'm going to cover the analog to digital converter and the digital to analog to digital converter, digital to analog converter. There are a whole host of screens where you configure the system to meet your requirements. This one we're looking at is the audio, the control for the audio input and output blocks, and the basic functions are over here. And you have a choice, a pull-down list to select all the sources that Spectrum Lab can see plugged in to your computer. So you select the source that you're going to be dealing with. And always, whenever you make a change with Spectrum Lab, there's an apply button, which if you don't hit, it will ignore you. So always bear that in mind. At the bottom here is the ability for you to tell Spectrum Lab whether the data is coming in as 1 byte per sample, 2 bytes per sample, or 3 bytes per sample. It's usually 2 bytes, but it depends on your source. You have the choice of working in mono or stereo, or I should say that should really mean 1 channel or 2 channel, because these slides are taken from a system that's being fed by a software-defined radio. So we've got 2 channels of data, but they're I and Q samples, which takes us on to this point here. Over the past few years, with the advent of SDR receivers, there's an additional function that's been built in for you to adjust the gain and phase of your left and right channels inside your computer to get the best out of SDR radios. The sampling rate. So this is driven by what your source is capable of doing, but it's also relevant to what you want to look at. So we'll talk about that in a second. There's a very wide range of sample rates available to choose from. The typical sound card in a computer works at 48,000 samples per second, so a sampling frequency of 48 kilohertz. But you can get external USB sound cards that work at 96,000 or even 192,000. And the advantage of those is that it gives you more bandwidth to look at. You can look at a wider range of frequencies. I do recommend for SID detection that you use one of these external USB cards for the reason that you can put it at the end of a USB extender cable. And I have mine at the end of an active 15-meter USB extension cable. So I can place my loop antenna well away from sources of interference. 192K sound cards, they do exist, but they're expensive. A 96K, I think, is a good compromise on performance and cost. I would bring your attention to this reading of 44,100, which is the compact disc sampling rate. If you use an external sound card, it is very likely that Windows will configure your new card to 44,100 when you plug it in. This is bad news. You don't want a different sampling rate in your sound card to the rest of the system. So if you add a new USB card, go into Control Window in Windows, look at the new device, and make sure the setting is at 48,000 or 96,000 if that device supports that operation. Okay, onward. The decimation function is useful. If you've got a source that can only provide 48,000 samples per second, which will give you a bandwidth of 24 kilohertz, so that statement again, but you only need to look at 6 kilohertz or less for what you're interested in, then you can decimate that input. In other words, throw samples away. And in this case, we're throwing 3/4 of the samples away. The advantage of this is that it lowers the demands on your CPU for the rest of the process. So you save CPU resource for use. I'll give you a demonstration of that right at the end, I think. The rest of this screen really is taken up with calibration of the sampling rate in your computer. Some applications require very precise timings, not the ones we're dealing with here, but other applications. And this is an informative window. And to show you the results of your operations, you can see the sampling rate here is defined to 3 decimal places. Spectrum Lab provides a lot of functionality to use an external source, say a GPS source, coming in through the right-hand channel for Spectrum Lab to actually discipline your sampling rate. Good, we've got the input and output blocks out the way. Onto the filter in each path. This is the control window for the filter block. You can see the response of the filter in this window. I've got it set as a bandpass filter. So it's only allowing a certain amount of the frequency range to go through. There are other options, of course, that you can select, low pass, high pass, etc. You can even feed in your own custom filter profile through a file. You set up the frequency and width of the filter here. A lovely thing about filter design in the digital domain is you can do incredibly sharp cutoffs. What we're looking at is selecting the output of frequency bins. And we've already seen frequency bins can be less than 1 hertz wide. So you can get cutoffs that are just unimaginable with discrete components. So whereas here we've set up for a 50 hertz slope range cutoff here, actually that's about 30 bins, and we could go a lot sharper than that. Another function of the filter block is that we can translate blocks of frequencies. We can cut a block of frequencies using the bandpass function, and then we can move them down or up. And this is the sort of basis of the BAT detection back voice listening process. You sample out a block of frequencies that are above audible hearing and translate them downwards. We're looking at the graph screen here. There are other ones available here, which I am not going to cover, except just to note this options screen here. That is when you're using an SDR receiver, the process of bringing I and Q samples together to provide your output is done in the filter block. So you need to tell the filter block that it's got to look for I and Q samples from two inputs. And you can also provide I and Q outputs from Spectrum Lab if that's what your application needs. Lots of other things here. This is there's a very effective auto notch facility down here, which I thought was going to be useful for meteor scatter applications in moving signals. But unfortunately, it only removes static frequencies. It doesn't track a frequency and move it as it drops through your the frequency range that you're looking at. But anyway, onward. Okay, there isn't a block on that schematic saying FFT because it underlines everything, but I ought to say something about it. So we have talked about the importance of the block size going into the FFT process. We have a wide range of choices of the number of samples that you feed into each FFT calculation. We also have a choice of window function. I showed you one curve that's used to suppress the samples at the start and end of the block, but there's a whole variety of different window functions which are suitable for different types of signal. So Han is the one that I've always used, but there are a choice of other ones. Once you've set that up, then this is another informative window. Spectrum Lab tells you the results of using those FFT settings along with the sampling rate. So you can see here that with these settings, each FFT bin is just under 1.5 Hertz wide. We've got a sampling range of up to 6 kilohertz. This comes from the fact that we're sampling at 12 kilosamples per second at the moment. It takes us about 0.7 seconds to collect those samples. Now, here I've overlaid a second calculation, this time using a block size of 32K, so we can compare the different values. So 1.5 Hertz bin width here, 1/3 of a Hertz, 366 millihertz bin width here. The penalty is that whereas our time resolution was 0.7 seconds, 682 milliseconds here, it's gone up to 2.7 seconds here. Okay, back to here. As I mentioned before, you can use Spectrum Lab with SDR receivers, but you need to tell the FFT process what sort of signal you're dealing with. If you're dealing with a straightforward audio signal, a straightforward analog signal, then you would use this option, the real FFT, meaning real values, as opposed to the complex values that you use with SDR receivers. Similarly, on the output of the FFT, you have a wide range of choices of the units that you're going to work in. You can either use linear or logarithmic scales and a variety of them. This is all just computation within Spectrum Lab to convert from one basic measurement to a variety of units on the output. Okay, there are some blocks in there which are purely to do with amateur radio functions, and I'm going to skip over those. There are amplification or gain control units on each channel so that you can select the levels prior to mixing. The gain is selected by this slider control on the right-hand side. And in turn, the slider control is what the slider control is driving is selected with these blocks down here. So you go into this pull down list, which has literally 100 or so different sources. You can apply this slider control to variables in virtually multiple variables in all of these blocks. So you can select the slider control to a particular variable using this setup here, and then slide it up and down to see the effect. The block that's colored blue, wherever it is, has got the slider control assigned to it. There are also some mysterious blocks here, quite small, looking fairly insignificant, which is not true. These are the black boxes. And the black boxes are repositories for applications, specialist applications that have been added over the years to answer some one particular specialist application or another. I'm not going to go through these. There's a huge range, as I say. I can see the use of some of them. Bandpass filter, for instance, you could use that to limit the frequency range of your signal before it goes into the FFT process and avoid that folding back of energy that I mentioned. Limiters, noise blankers are typical digital signal processing processes for radio use. This is an interesting one. This was an experiment carried out by AMSAT Germany, and AMSAT is the amateur radio organization that deals with building and operating amateur satellites. This is an Earth, Venus, Earth. This is Venus bounce, not moon bounce, Venus bounce. And the guys successfully bounced a signal off Venus. So, and Spectrum Lab was used as part of that setup. Other things, well, I can imagine a delay echo line be useful if you're looking at multipath effects, modulator, demodulator, de-emphasis with FM radio signals. Correlator, there is a direction finding application within Spectrum Lab. So hum filter, etc. So onward. Explore these at your leisure, I would say. Back to that block diagram again. That's an interesting one. Just seems to be there. No idea what happens to that. Actually, it's the function that allows you to concatenate the two chains. So you can put your signal through this chain, then you can link it and put it through this chain, which doubles up, gives you 8 black boxes to play with, gives you 2 filter mechanisms. So if your application needs that level of complexity, it's there. Right, and we will go for our second video, which I hope works, and then I'll stop for questions.
Here I have the same signal generator setup that I used at the start of the workshop, with the signal generator producing 3 separate tones. So I'll simplify it by just taking off 2 of those tones to leave a pure sine wave. What I wanted to demonstrate was the modulator or modulation functionality that's also available. So we can apply some amplitude modulation to this signal. So we have sine wave modulation here. There's a range of other waveforms that we can use. So if we go to rectangular, for instance, we get that. So this has got 50% duty cycle at the moment, so 50% on, 50% off modulation. If we come down to, say, 5% or lower, then we end up with short bursts of carrier. And these can be quite useful if you're testing the meteor scatter event detector, for instance. You would think if you're putting equal bursts of equal amplitude signal into the system that you'd get equal measurements out of it, but you don't because of the window function issue. So it's quite useful to actually be able to demonstrate that. But okay, that's amplitude modulation, so we'll take that off. And we can also apply frequency modulation. So here I have a carrier of just over 5,000 hertz, and I'm modulating it with a frequency of 100 hertz with 2,000 hertz deviation. So quite severe, but sufficient to show the principle of the system working.
Right, so that concludes the section on the signal processing. So I wonder if there are any questions.
Yes, Paul.
I've got a question. Oh, go on, Norman.
Looking at it in terms of VLF radio, if we put an FM signal, a variable frequency signal, you're sweeping in a band, will you be able to extract that signal and see what the effect is on the equipment? Perhaps I'm not correct.
If you've got a sweeping VLF signal, obviously within the range of the sound card, then I'm guessing, I've never tried this, but I'm guessing you would need to set up things like the Windows overlap function and whatever, and sampling rate to illustrate that.
Well, developing that, we've got 2 channels on Spectrum Lab. If we had one channel generating a signal and you applied that to a VLF receiver at the same time as you're playing, and you looked at the output, you could see the output changing with respect to its tuning.
Well, you could certainly measure the frequency response if that's what you mean.
Presently, I'm constructing a Chinese signal generator. Rather, I'm not constructing it, I'm adapting it to give me a 1 hertz to perhaps 100 hertz signal source. So,
yeah, well, certainly
at the moment for Spectrum Lab.
Certainly, Spectrum Lab would be useful in actually looking at the output of that and following your work.
Up to the limitations of your sound card.
Yeah, okay.
Thank you, Paul.
Paul, I had a question. Have you played with the various functions of FFT windows? I've played with them on various SDR things and never seem to see anything changing. Every FFT application seems to have these. And I've never spent the time like you've obviously spent with Spectrum Lab. And I just wondered if you have any practical information of what things like Han, etc. do.
No, is the answer to that. I haven't had the time. Sorry.
Okay. it'd be great if somebody knew, had some information, because you've got so many different window functions, and it's obviously to do with the sort of artifacts you see in the results, but it's quite complicated, I suspect, to understand the results.
Yeah, there was. I think we're probably all familiar with the image of the black hole that came out. Was it last year or the year before last? I can't remember. And in the news articles covering that, there was reference to somebody who was processing the data from all of these radio telescopes to get the optimum result. And it did occur to me that she was a young lady, I seem to remember. She might have been playing around with the window function to see which gave the best image.
Yeah.
Any other questions?
I don't know whether you saw that. I think I don't know whether you saw the chat, Paul, but I put a note up about the answer to using the video GPU to process FFTs, and that was something that came up at an RSGB conference a number of years ago. Eben Upton of the Raspberry Pi organization was asked, can the GPU on a Raspberry Pi be used for FFTs? And I presume at the time he must have said no, but then a library appeared a month or two later. So if you want to do FFT processing on the Raspberry Pi, you've got a very fast application that can do them in the GPU, which could be quite useful.
Frustratingly, I can't find access to the chat channel when I'm in full screen sharing mode. So I'm very sorry, but I can't see the chat channel. I've been looking for it as we go along. But
I do have a question. I've been working with GNU Radio and to do collect pulsar data. So we collect it with the GNU Radio with an SDR, and then we output it to what they call a .fil file, and that .fil file gets sent to a program called Presto, which analyzes the data and converts it into the standard pulsar pictures. This looks very close to what GNU Radio can do right now. Have you seen GNU Radio and compared it with this?
No. GNU Radio postdates the development of Spectrum Lab by a decade, probably. So I'm not at all surprised that there are other applications that can do what Spectrum Lab does that have come along, yeah, okay.
Actually, Paul might want to chip in as well. The other Paul, we're actually having a new radio workshop in a month or so, a couple of months. I can't remember the name of the chap.
Yeah, Marcus Leach.
Yes, thank you.
Okay. Can you output the data from Spectrum Lab into a file that you can process with something else?
Excellent. Thank you for that. If you could just hang on a couple of minutes, I'll show you.
Great. Thanks.
Okay. Shall we press on? Right. Actions. Okay, we've seen the flexibility of Spectrum Lab, the different blocks, the different way they can be configured, set up together. We need a means of driving that, and that is the series of functions called actions within Spectrum Lab. Why am I not going on to the next slide? There we are. Right. Okay, so Spectrum Lab has these actions. There are three of them: periodic actions, which are actions that are taken at regular intervals; scheduled actions, which are actions taken at arbitrary times; and conditional actions, which are actions driven by other circumstances, and certainly the most powerful of the three. To use these actions, there is this command interpreter, which is built into Spectrum Lab, and that supports the scripting for these actions. The command interpreter is a bit of a bespoke beast and unforgiving, it's something where accuracy is absolutely essential, but it evidently does work, which I'll show. Okay, I wondered how on earth to do this. There are hundreds of functions within the interpreter. I decided to just go through the list and pull out one per letter of the alphabet. They really are spread all over the place. There are functions to take measurements coming out of the instruments and calculate values from them. There are functions to modify bits of the configuration on the fly. There are functions to carry out actions. There are functions to convert numbers. There are functions to support the programming principle. And there's the function to support the export of FFTs. And functions to directly configure blocks on the fly. Other functions, okay, so we've got programming support functions, etc. We're down to the letter M, go on to the rest. Now that's a very useful one for when you're doing timestamps. Queuing of events, remark. So that's so that you can remind yourself what the hell you put that in for, and so on. Range of arithmetic and logical operators. I will show you examples of how these are used. I just wanted to try and give some idea for the range. This is the first of the three mechanisms, the periodic actions. It's a very simple one. You can have lots of commands one after the other. This just captures a screenshot and saves it to a specified file path, and saves it either as a JPEG or a bitmap. That in JPEG controls the compression rate, so you can decide on whether you want detailed JPEGs or blurry ones. This sets up when the period for which this periodic action is going to occur. And what it does, it's part of the Meteor scatter one, and basically I save the screen. My screen will cover 4.5 minutes. So using periodic actions, I build up a series of JPEGs that cover the entire day, which allow me to check whether an entry in the event log is a meteor or whether it's an interference phenomena of some sort. And also, if you get a really nice big event, it's nice to have the image. And of course, there's a button to switch it on and off, and that can be very frustrating if you don't tick it when you after your change. The next screen is the scheduled action, which allows you to just put in actions at certain times. The single word capture, without anything after it, will capture the screen to a, what do they call it? To a predefined path, predefined folder, which you set up as part of the configuration. I used this to capture an amateur radio beacon at certain times, specific, so that I could measure the frequency stability of the receiver. I just measured the beacon frequency at certain times of the day, and then came back later and just saw what sort of variation there was. Again, the active window. And this is the conditional actions. You can see 2 orders of magnitude above anything else. How do we work through this? We don't. We'll do a little bit of a sample, but this is a whole subject on its own. In fact, this is the conditional action script for my conditional action script for Meteor scatter. Oh, not Meteor scatter, Meteor reflections, Meteor scatter on the brain. On the left-hand column, you detail the condition that you're looking for. On the right-hand column, you specify the reaction that's to be taken. And the script just continually cycles through all of these and performs your absolute desires. Let's just take a couple of quick samples. This is at the start of the conditional action script. Here is just a label, remark, and it's just to identify this version of the conditional action script for reference, time it was saved and date it was saved. We then have a whole host of initializing lines, which are only run once at the start of when you first load the application. And here what we do is we identify the variables that we're going to be working with. We assign values to them. This particular line of variables are ones that would be unique to a user situation. So I've got the start of the comment here, remark user to set these. So there's a center frequency, which is where the meteor would happen if it occurs. There's a print frequency, which specifies where the things appear on the output screen. And there's a trigger level, which is a sort of sensitive adjustment. Through here, we can do some simple calculations. Okay, so we declare a variable here, trig low, and we do a bit of an arithmetic calculation. Basically, this instruction and this instruction sets up a trigger channel of 100 hertz below the center frequency and 200 hertz above the center frequency. And if the system sees a burst of energy within that range, it triggers. And we start to define a noise channel, an adjacent noise channel in the next one, so that we can do some calculations later on. We reset flags that we use in the rest of the process. Yeah, remark clear state flags, just reminding myself what they are. Here's another variable, trig time. We set up, it's going to be obviously stored as a timestamp. So we define the format that we want to the timestamp to be in. Interestingly, in this application, I've defined it to 2 decimal places of a second. I've worked up to 3 decimal places time-wise in Spectrum Lab to follow an instruction through the system and anything else. Okay, and finally, we start our timers running. I use a number of timers for this. So there's 9 timers within Spectrum Lab, and this one is just a single shot timeout. This one fires every 10 seconds and so on. So that's my first brief description of the sort of things that you do. Okay, this is another block line 9 here up at the top, we see that the timer number 3 is expired. What happens? Well, first of all, I set a flag, which tells the rest of the script the system is now running. And I print to screen a message, which says system start and identifies the configuration that I'm using for this particular instance. Line number 10, okay, if the system is running, R equals 1, and if we've just had a new FFT calculation come out, then we start to take a new set of measurements. So we take something called NSE, noise, and it's the noise measurement across the noise band. Here, we take the variable sig for signal, and we assign to it the peak value of any energy in the trigger band that I referred to earlier. And then I go on to make a calculation. This line goes on somewhere to the edge of the room that you're sitting in. And then this block here of conditional actions. This is my methodology for getting over the window function issue. Okay, you can run FFTs quicker and quicker and overlap them to solve your visual impact of spectral bleeding. But doing that alone is not sufficient, because the way this system works is that one FFT will trigger the whole system to say, hey, there's a meteor there. And that one FFT will be the one that will measure the strength of the signal. But that's no good, because that signal might just fall within the start of the block and be artificially suppressed. So I've implemented this function where actually sig max is the measure I use, is the maximum value of the trigger FFT plus the following 2 FFTs. Now you may say, oh, well, you're going to miss the start of the event, but you know that the value is pointless if it's been played around with the signal function. And the FFTs are running really, really quickly. So this sig max concept of the maximum value of the first 3 FFTs is a much more reliable way of measuring the signal and comparing it with other people. So that's my strategy for doing that. What else can I say? I can just read through a line. So if the system is running and if the variable signal is greater than the variable trigger and these flags have been set, oh, that's a wrong line to choose, Paul. Come back 13. So if the signal is running and signal is greater than trigger and these flags are set, then put the value of signal into sig2, and then the following line, if sig2 is greater than sig max, then update sig max to the bigger value. So that's the basic concept. Well, I'm sorry that I can't go on through the rest of the script in detail, but my voice is starting to wane, and from those people, I'm surprised quite a few people are still awake, but I hope that gives you a flavor for the flexibility of the conditional actions system. There is debugging support, I'm pleased to say, and if you're developing your own script, you will need it. So you have the ability to pause and step through the system with variables coming into these windows. You can insert breakpoints to identify what happens when you go down some side route. So that functionality is there. And that concludes that part of the system. I'm just checking the time here. So we've been going for an hour and a quarter. I've probably got 45 minutes. An hour left, I think. So I don't know if people would like to ask questions, and perhaps if we could have a short break. I'd like to go and get a hot drink, but I'll take questions first, if that's okay. Maybe you are all asleep.
No, not at all. I think it's worth mentioning that the most of the windows within Spectrum Lab have a help function, a help button at the bottom, and the help is very comprehensive. I don't know if you want to make any further comment on that, Paul, but it is really helpful.
Next section. It's in the next section.
Okay, good.
If that's okay, could we take a short break and restart at 11 o'clock? Is that okay with people?
Yeah, good plan.
Fine.
Okay, 11 o'clock restart. So I am back. I've selected the output of Spectrum Lab that I've got running at the moment, just as a filler. We're actually looking at the amateur radio beacon, GB3 VHF. Very poor signal because it's a VHF beacon being received on a UHF antenna. They're useful facilities, these beacons, because this part of the spectrum, the horizontal bit, let's see, can I trigger a, you can see the terrible jerky motion. This is why my videos failed. It's just that there's too much detail on the screen and Zoom just cannot keep up. But the center line in between the tone bursts is a precision fixed frequency, GPS controlled, so you know it's precisely 144.43 megahertz. The tone bursts, which happen every 2 minutes, provide a nice way of confirming that it's the signal you're after. It's very distinctive. Their purpose is to, the beacon is used as part of propagation studies from stations a long way off, and the tone sequence allows them decoding of the signal under really poor signal to noise conditions. So there we go. And it's driving the event detector absolutely crazy because the event detector is for meteors, not for amateur radio beacons. Right, I will now attempt to come back to presentation. Right, sorry about that, but I've got I probably should not have changed screen, so I'm just going to panic. exit full screen. That allows me to go back into PowerPoint. That allows me to come back to the point at which we left it. Otherwise, we would have had an hour and a half repeat of what we've just been through. Sorry about this, being too clever. Okay, so I will go back into Zoom. Right.
Looking good.
Yeah. Woo! Sorry about that. That's something I didn't rehearse. But there we go. Welcome back, everybody. I think we've still got people out there. Yeah, 24. That's good. Thank you very much. Okay, so now I'm going to finish off the last piece of the functionality bit by looking at the configuration options of Spectrum Lab. And then finally, I'll do demonstrate the sudden ionospheric disturbance and meteor scatter application. There we go. Right, so configuration. The factory default is the screen. We have a spectrum graph at the top. That shows you the output of each FFT calculation as it happens. So this is the spectral content of the signal coming in. The frequency range depends on the sampling rate that you've got set up. I told you you'd be getting fed up with me talking about sampling rate, but it is so important. So at the moment, when this was taken, the system was obviously set for 11K sampling rates, 11,000 samples per second. We've just got a frequency range of 0 to 5 kilohertz here. And then after the FFT displays the calculation, that's moved to the top line of the spectrograph, also known as a waterfall. And as we'll see later, I think that's a much more appropriate name for it. And the waterfall just gradually descends down, and so you can see the history of the signal. Interestingly enough, if your screen cursor is not in this area and it's down here, then this graph will show you this line, not the new one, but you can actually go back through the waterfall and examine each line at the top here. Right, okay. We have a number of controls down the left-hand side, which I'm going to deal with first, and then I'll cover the menu headings across the top. So this is the top left-hand corner. We have 3 windows to enter information here. The first one is labeled VFO, which is something to do with radio technology. Basically, you can apply this offset, this figure here, to the frequency scale on the right-hand side, which you can't see at the moment. I use this to position the frequency at which zero Doppler shift happens. So the carrier frequency of the Graves radar, for instance, at a frequency of 0, and then that gives me a visual readout of Doppler shift straight off. But that's just personal preference. FC is the center frequency of the waterfall display. SP is the span. So at the moment, we're looking, the display would be centered around a frequency of 2.48 kilohertz. That's the frequency coming out of the, because I'm using a an SDR receiver at the time, that's the center frequency. That's the frequency coming out of the FunCube dongle. So we're looking at signals around 2.5 kilohertz coming out of the receiver. And we're looking at 750 hertz of spectral bandwidth. The buttons underneath provide you controls so that you can zoom in, zoom out, change the frequency range, change the sensitivity, etc. This option button here allows you to include that VFO offset or otherwise. And you can see a number of other options here, which I don't use, and certainly things to do with remotely controlling rigs, in other words, amateur radio equipment, are not appropriate here, but we'll press on. The bottom half of the left-hand column contains 16 configurable buttons. So you can use these to either display information or actually initiate actions. If you right-click on any one of these buttons, you pull up this screen here. The top line allows you to define the name on the button, and then the center line allows you to insert a command using the interpreter. So in this case, when we hit the button labeled Capture Now, we fire the capture command, which does a screen capture and saves it to the path that, well, actually the path is predefined, but the file title begins with CAPT and then has a timestamp in that particular format. Choose another button, event duration. So here it doesn't do anything, it doesn't initiate any action, but it just does show the value of a variable from the conditional actions screen. So in this case, it shows the variable mdurn, meteor duration. It would have been the last meteor event in seconds. And finally, excuse me, we have this one. The title is signal generator, and then I toggle between signal generator equals off and signal generator equals on. And in the line beneath, that's an actual command to switch the signal generator on and off as I click on that button. I have the signal generator put a tone out at the carrier frequency that I'm expecting to see. So effectively, I can create an artificial meteor, even if I don't have an aerial connected. So that is a very useful test facility if you're getting started, to make sure you're looking in the right place and everything within the laptop or within the computer is working fine. I can also check the event log to see that that's a test event has been logged there. Okay, and then that's the side controls. Going across the top, we have a number of options as usual. So I will cover a couple here. Start and stop does what it says on the can. It is worth noting that it's stopping the sound thread as well as stopping the display also stops other functions like the signal generator and the input-output monitors. It sounds obvious, but it represents a conclusion from probably 2 hours of investigation. On the right-hand side of it, you have the help facilities that Paul Hearn was referring to. So the user manual for Spectrum Lab runs to just under 300 pages. There is an awful lot of information in there. It's not the easiest of reads because it's been added to in the same sort of timescales as features have been added to Spectrum Lab. So it probably covers about 15 years or something like that. But there's a lot of information there. If you get stuck, then that's the place to turn to. This gives you straight into the user manual, either at the front or at the relevant chapter that you're looking at. Okay, now we'll move on to the file heading on the left-hand side. And this gives you the basic tools to stop and start the system. Directories is just the default folders which you set up when you first use Spectrum Lab, or in preference, just leave them be. It's just where you can find the folders where things like screenshots will be saved by default. Screen capture we've already covered, as that just really replicates the button that you press in the left-hand column. Though using this function, you have the option to either save it to the default folder, or you can browse to another folder and then save the screen. Load settings from and save settings as. This is such a crucial part of Spectrum Lab. If you're changing applications, this is how you set up Spectrum Lab. It takes you to a configuration folder in which there is a huge number of configuration scripts that come with the factory install, and to which one or two are added. These top two are mine, and everybody is welcome to these if you're interested. Otherwise, there's a range of scripts running down several pages. And as I say, that just configures the setup to do what you want it to particularly do. Somebody asked about exporting the Fft spectrum. Well, you can export it as a text file, which is probably not what the question was about, but I have used that function and imported FFTs into Excel, because I'm not very familiar with all these new tools. So I just shove a line of 8,000 samples into Excel. This was part of an investigation into whether I could find some way of detecting aircraft reflections by their spectral signatures. So these are 5 FFT outputs, one after the other, and looking at the way the spectrum has changed. And I maybe some characteristics there that would distinguish an aircraft reflection from a meteor one. But I failed in that endeavour. Hopefully somebody that's a lot cleverer than I would come up with an answer, because aircraft reflections are a bit of a nuisance when you're trying to detect meteor reflections. Okay, and then you have a huge range of colour palettes available for the display. The one that's standard for the factory default is one called Sunrise. There are others quite weird. I don't know what Jim was on when he devised this particular colour scheme, but I'd like to avoid it. So as I say, yeah, it's interesting. Some of them are quite useful. The white to black down here at the bottom and black to white just gives you a black and white visualization of the screen, which can be useful. Right, okay, I should have mentioned one other. Can I go back? Yes. The bottom two lines, exit does what it says. Exit without saving. When you exit Spectrum Lab, it will reopen with the same configuration. You can exit using the bottom line or the right hand, like everybody does, the right hand screen corner. But if you want to exit without saving your configuration, then use the exit without saving option. But nobody ever remembers that. Right, into the options menu section. This gives you access to the various configuration scripts. We've already had a look at the audio settings and the FFT settings. The Spectrum display settings, there's a huge range, which we're about to go into. but a fairly fast run through in the interest of time. Here's screen number 1 of 4. You will see you can do just about anything and a few things you can't think of. Let's just go through the important ones that you really need to know. This one gives you the ability to just show the waterfall display, or perhaps just the spectrum graph display, or both, as most people do. There's a 3D spectrum option, which some people find good for looking at meteor scatter. Yeah, I'm not too fond of that. I don't think it actually adds very much, but it's a sexy representation, so some people like sort of looking at it. And down here, we talked about window overlap and the scroll interval. There is an automatic setting in Spectrum Lab which relates the waterfall scroll rate and the overlap. I suggest you leave it as it is, but you can go into other options. You can, for particular purposes. Many of those options lead to a very jerky scrolling rate. And there is a checkbox there that you can apply, which smooths the transition out, but at the expense of giving your CPU a hard time. And then you can set up the waterfall time grid. Lines, that's entirely up to you. The most useful thing, I think, is defining the interval period, the markers, which is 60 seconds here, but actually I use 20 seconds and 5-second time interval markers on the waterfall screen, depending on the application. The rest of them cover whether you want the grid showing or not, double width, waterfall lines. Oh, there's so much. You can define the size of some of the windows, and it's a good evening's entertainment. Screen number 2, the most important thing here is the brightness, and I don't remember actually covering the brightness and contrast settings on the top left-hand corner of the screen. I am very sorry about that. There were 2 sliders in there underneath the 3 settings for frequency center, span, and whatever. But there are 2 sliders under there. One's labeled B, which is brightness, and one's labeled C, which is contrast. And that would have driven the screen representation, what appears on the screen. But they're fine adjustment sliders. If you want, if you've got wildly different signal levels, then you can set them up in this window. So this is number 2 in the spectrum display. Visual AGC is quite interesting. If you have a very, very noisy picture, it is quite interesting to apply visual AGC. All of a sudden the noise disappears and from behind it appear meteors. It's quite miraculous, but not something, AGC is not good news for radio astronomy applications, so generally leave it off, but it's an interesting function. Don't think there's anything else that's important. Dedicated users will find something, but there we go. And when we get to configuration, this is the bee's knees. You can do your own screen design. Using this screen, you can change background colors, you can change pen colors, you can change the font of your scales, you can change the font size of the scales, you can change whether the label appears above a transparent background or is overlaid on the background. You've got the separate controls for the spectrum graph and the frequency scale. No, sorry, waterfall grid. So again, you can define all of these things. I found it useful when I want to take screenshots and put them into a document, because black backgrounds is bad news for that sort of thing. So it's very useful to capture everything on a white background, black pens on a white background, then you can do a screenshot and just copy it into a document, or save your printer for that matter. Okay, so that's screen number 3. Screen number 4 is predominantly the 3D setup, which needs its own adjustments. So let's go back. I don't think there's anything else. The parallelogram, yeah, I think I pronounced that right. I guess is related to the direction finding application within Spectrum Lab, which I haven't played with. Okay, so we're back with the options headings. We've just covered these spectrum display ones. Various others I haven't used. System settings is an important one. Click on that, you get this script, and the important one is this one here, because is my cursor showing? Right, that one there. Okay, because that allows you to lock your system Spectrum Lab to UTC time as opposed to the computer time. So by checking the box here, gives you a choice of either taking the time zone information from the computer or using it with that. And I lock to UTC, which everybody should do if we're doing radio astronomy applications. Another option, oh, we're on to quick settings. We're on to quick settings. Right, so this is the, I think the fourth one along the menu option. These provide you with a range of configurations for different applications. So if you're interested in doing radio equipment tests, then load the radio equipment test quick settings. If you're going to be working with an SDR receiver, then there's an option there. I would say that support for SDR receivers, software-defined radio receivers, is limited. I use a FunQ dongle, but that's pretty unique amongst SDRs, because in that the output looks like a sound card. Although it's IonQ data, the format is the sound format, so it can be just treated. My voice is starting to give out, sorry about that. If you do have an SDR receiver, one option is to use something like SDR Sharp, and then use a virtual audio cable to route the signal from that into Spectrum Lab. Excuse me. What else? Oh, and possibly the most useful setting on this list is down here, restore factory settings. If you get yourself into a mess, hit this and you come back to a new version and can start again. Right, we're onto the component screen. This basically allows you to switch on and off various bits and pieces. Whenever I brought up the block diagram of the system, that was by clicking on this show components option at the top here. You can switch on individual blocks going down through here, or you can switch them on via the circuit window, via the show component screen. So I hardly ever come in here apart from just to bring up the component screen and perhaps the filter control window. Those are all blocks of information, blocks of functionality that you can switch on in the component screen. If we go to the next one, which is the view windows, that's pretty much the same as, but controlling the different windows. So I've been just looking at the spectrogram window, the waterfall window in the displays so far. I haven't been including the spectrum graph or amplitude bar, and we haven't been looking at the radio direction finding application, which I guess is what the parallelogram is to do with. We can switch off all those buttons on the left-hand side if we want a full screen side to side, or we can, in addition, switch off the titles across the top if we want full screen display. The watch list and plot window, I'll be covering those under the SID, the Sudden Ionospheric Disturbance application. So we'll demonstrate those later. Coming down this list, there is a debugging window showing you information about the system. If you need this screen, you're in trouble, but it's there. The CPU load screen, that's actually quite useful. I'm going to demonstrate two versions here. It shows you the amount of CPU capacity tied up with each of those blocks. So you can really understand how hard your processor is working as you configure each of those blocks. I've done two side by side here to show the effect of decimation on CPU loading. So the one on the right is with decimation set at 4. So I only need a quarter of the samples, so I've thrown 3/4 of them away, which means that I need additional CPU capacity on the input decimation block here. I need an extra 3.6%, but after that, then I'm saving all the way down the line. And the end result is that the loading drops from 27% to 8%. This is of a CPU core, I believe, not the CPU total. Otherwise, it doesn't tie up with the idea of 21 instances running at the same time. Good. We are now into the last section. I'm going to demonstrate with a couple of videos setting up the system for these two applications. Oh, yes, I should stop for questions. My apologies. So are there any questions for the configuration stuff that we've just covered? Right. Onward. So the first application that I'm going to deal with is sudden ionospheric disturbances. So the aim here is to detect solar flares through their effect on the ionosphere and then the VLF radio transmissions. The VLF radio band, if you look it up, it says 3 to 30 kilohertz. So your standard sound card will cover up to 24 kilohertz. And you can easily get an external card that will cover up to 48 kilohertz. So that makes a perfectly adequate VLF receiver when used with a loop antenna. And whenever I give a talk to astronomical societies, well, in the good old days, there's always confusion when you start telling them to connect the loop antenna to the microphone socket. There's much scratching of heads. But of course, a loop antenna is just a means of converting radio waves into little tiny electrical signals. As a microphone is just a way of turning sound waves into little electrical signals. After that, they're little electrical signals. Right, so what we need to do is measure the amplitude of various transmitters, and then we can look at these in a spreadsheet or data plotting application. Here we have the factory default setup for Spectrum Lab, and you can see my voice coming in through the laptop microphone and over a frequency range of 0 up to 5 kilohertz. So how do we convert this into a SID detector? Well, instead of a microphone, we want a loop antenna. But that's pretty much all we need in the physical sense of things. we plug our loop antenna into a microphone socket. Now, I recommend that you use an external USB sound card on the end of a USB extension lead, because then you can locate your loop antenna away from the laptop or other possible sources of interference. And that's the arrangement I've got here. So let's get started. The first thing we do before we plug that loop in is to go into, if we go into File, Load Settings From, and select the SID configuration from the list of files there. Open that, and we see things change. We don't want that. What we see is an awful lot of nothing at the moment, plus an additional screen down here, which we haven't seen before, but I'll say a few words about that in a minute. Okay, the reason we're not seeing anything is because we're now looking at a completely different frequency range. We're looking at from 16 kilohertz up to 27 kilohertz. So our microphone input is producing energy way down at much lower frequencies than this. So to rectify that, we'll go into Options, and we will select Audio Settings. And there we see we've got our laptop microphone input. And what I'm going to do is go into here and go down the list. And here's my external USB card. So I will select that and apply. And almost immediately we start to see the VLF radio stations begin to build in the spectrogram and start to appear on the waterfall. What we're looking at here is a number of VLF radio transmitters. So we can come along the list here. This one at very weak one down here will be in Norway. This one here, 18.3 kilohertz, I think is a French station. Desperately looking for my list. 18.3, Rosnay. 18.3 kilohertz is Rosnay in France. We're missing one of the usual stations, Anthorn in Cumbria, which is at 19.6. That tends to go off at night at the moment. We have another one here at 20.27, I think, and that'll be down towards Italy. This one here at 20.9 is Saint-Assise again in France, and here we have 22.1, which is Skelton, another VLF transmitter up in Cumbria. We can just about see the German station here at 23.4 kilohertz, which is Rodophen. Right, so depending upon the state of the ionosphere, we will see very different shapes throughout the day on here. And this is the whole point of SID detection. What we're doing is using these VLF stations to get some idea about what's going on in the ionosphere. Now, to do that, we need to monitor the amplitude of these stations. And obviously, what we need to do is do that automatically. So we do have something in Spectrum Lab to do this for us. And if we go into View Windows, we can come down to something called the watch list. And we will focus on that. So here we have we've zoomed into the watch list. And what this function does is allow us to put in a number of instructions to measure the amplitude of the signals coming in. So we have up to 8 channels, I believe, on the watch list. And for each one, we have a title. For each pen, we have a title here. And I've simply used the frequency of the transmitter as a label. So going from 19K6, so that's 19.6 kilohertz station, up to 37.5 kilohertz, which we can't see on the current display. And against each of these, we have this expression, which monitors and measures the amplitude of the signal. And what we're doing is we're looking at individual frequency bins. If we look here, this first line, we're looking at the frequencies from 19.525 to 19.675. So that's, let's see, 150 hertz. So what this instruction does here is calculate the average of the 100 frequency bins that lie between these two frequencies. We then multiply that by a factor depending upon how strong these signals usually are. So for very strong signals, and when 19.6 kilohertz is present, that is usually a very strong signal, I've got a multiplication factor of 15,000. Basically, it's just to get a sensible reading as a result. We do this for all the other frequencies. So for 20.3, we're measuring between 220 and 280, 280 hertz, and going down up to 37.5 kilohertz, we measure between 37.425 and 37.575. And we use different multipliers down here really to get sensible readings during the day for the result. That helps us with the plotting. We can specify the format of the number that we save for this. So I'm just using one decimal place here, and we can specify a scale value on which this is the results are plotted. So where do we plot? Well, we have a facility here called Plotter. This is the screen you saw earlier. It's a bit of a mess, I'm afraid, because I've been switching this laptop on and off all through the day. So, and in fact, over a couple of days, we've got 15th of May here, 17th of May here. We've got 18th of May here. Normally, these would be solid lines showing the strength of the individual carriers, the individual signals throughout the day. When you get a sudden ionospheric disturbance, then it becomes quite apparent on this plotter graph as to its existence. What you're looking for are changes, significant changes that occur, that happen to to more than one transmitter. You're not interested in changes where in just one single trace, because that could be maintenance work being done at the transmitter. What you're looking for is a change in the shape of the curve that affects two or more of these VLF stations, because that then indicates that it's down to changes in the ionosphere. Now, what you want to do is to actually monitor the shape of these changes for sudden ionospheric disturbances. And although this plotter function is reasonable for showing you that there has been a change, it is not really suitable for actually making a measurement. So what I do is to actually export these readings and then import them into, in my case, Excel, and use that for making the actual measurements. So how do we export these readings? We can see them in the plotter, but what we need is to get them out of Spectrum Lab and into something else. And this is where the conditional actions come in. So if we go into the conditional action script, and I'll bring this down here. It should be visible. and open it out. And we can see a very simple set of instructions in the conditional actions. We have an initialization line at the top here, which basically we set a timer running, and this timer times out every 10 seconds. So that's the initialization line. The second line is driven by the timer actually firing. So every 10 seconds, this timer fires and kicks off these three actions to save the information. So the first line basically opens a text file. If the text file isn't there, it will create it. And the final character in this expression is basically to say that we are about to append a new set of readings to that text file. That new set of readings comes from the next line, which is a continuation of the same instruction. And basically it defines a timestamp, a format for the timestamp to go into the text file. It saves the current time into that format, and then it follows with a number of readings from the individual channels in the watch window. So we can see that we've used the same label here, 19K6, from the watch window. Basically, we're saying take the reading that's associated with this variable 19K6 in this format, so a single decimal place, and save it in a text file. Then save a comma, and then save the reading against the next transmitter, 20K3, 20K, 20.27 kilohertz. Again, followed by a comma, and so on. And once all the readings have been saved, then the final instruction is to close that text file, ready for it to be opened in 10 seconds later. And you can see the conditional actions firing every 10 seconds. You get that green flash as each instruction is carried out. So that gives a visual indication that things are working. Good. So now I ought to show you although it's not Spectrum Lamp functionality, I'll just quickly show you how I actually get the results charted and measurements made. Good. So this is the methodology that I put together about 15 years ago to get my SID charts. I've never got around to improving it, so please don't laugh. But anyway, that's what we have is the daily file, which contains all those readings as I just described. I simply import that into an Excel worksheet in this area. That's just 2 or 3 clicks. I have the ability to apply a multiplier and an offset to each reading. This is so that I can compare one curve against another. Of course, there are lots of better ways of doing it nowadays, but 15 years ago, this was the only one that I had access to. So these are applied to these readings and result in these readings. And then I just chart that output. This is a typical chart from a few days ago. You can see the output of the different transmitters, amplitude output, loads of hash during nighttime conditions when you just don't get reliable propagation because the sun isn't there, funnily enough. During the day, things settle down. But you can see various sharp changes in amplitude. This is always an interesting time, dawn. Lots of things are happening. The sun's coming up. All that ionizing radiation is hitting the ionosphere for the first time. Initially, it's illuminating it from the underside, from the underneath, as the sun creeps above the horizon. So you get wild variations in amplitude as the ionization levels change and the reflection of the radio signal changes. So if you have an event here, you've had it, because you can't really distinguish it from what's going on naturally. But elsewhere in the day, that's a sharp change there. That is most certainly a change in transmitter power, so you're not interested in that. This is a burst of interference. My induction hob is a good source of interference, so I know to ignore times when I'm doing something there. But the experienced eye can spot events, sudden ionospheric disturbances. I can see two. That screams at you straight away. Definitely changes there. And oh look, there's something going on with the transmitter in Iceland, and even one of the French transmitters. There's a hint there. So that looks an interesting candidate. That's a dead cert. That doesn't belong here. The characteristic SID shape is a shark's fin, as that level of ionization from the solar flare hits the top of the atmosphere, the ionosphere drives up levels, and then you get a gradual decay as it goes down. So those are two definite candidates. I then use the Excel controls to do a comparison. These are noisy signals because my loop is actually in a temporary location at the moment. I still need to get it shoved down to the garden shed, which should improve things. For SID monitoring purpose, you're only interested in three things: the start time of the event, which we can sort of just float the cursor over the curve in the Excel spreadsheet, and that pops up a time. The time of the maximum of the event, ditto, and the time of the end of the event. That's pretty subjective, and people have different views as to when the event finishes. So could it be here? Could it be here? Could it be here? So you just there is room for disagreement on that point. Lots of other events that aren't so unclear as this one. Here's another one. We're into the, this is 7 o'clock in the evening, so we're well into sunset time. Normally we would not be able to give timings for this event because they would be lost in the natural transitions as the sun go down. However, this dark blue curve here is a transmitter on the East Coast US, Cutler in the state of Maine, and that gives a correspondingly longer view, and we've just captured the event on the Cutler transmitter. So a clear start time, a clear peak time. I'd put the end time about there with the, yes, I think still there. And the rest of it is the sunset. So anyway, that's the sudden ionospheric disturbance process in its entirety. Sorry about the simplistic way. Oh, I should just say about the component setup. It's the factory default setup, but with just different frequency, sampling and frequency ranges. Bog standard, so really not difficult at all. Okay, so now we're going to move on to meteor detection.
Can I ask a question, Paul?
Yes, I thought that would be a good time, actually. Yeah, go
on. Obviously, this SID detection relies on the fact that these VLF stations exist and carry on. Do we know why they're there? I mean, are they still communicating with submarines and things? And will they carry on forever? Because when they're gone, you won't have a source.
Yes, you're right. That's the purpose of these transmitters. VLF radio emissions will penetrate several meters of seawater, so you can. It's the only way of communicating. Well, okay, you can communicate with submarines when they're submerged. I don't expect them to disappear until after the nuclear apocalypse.
Good one.
Any other questions related to the SID detection?
Yeah, Paul, can I ask a question? Just looking at your diagrams there of different stations you're receiving, with directivity of my loop aerial, I find I'm quite limited to the stations I can receive without actually turning the aerial. Are you using some method to spread the bandwidth, not the bandwidth, how do you call the word, the spread of the pickup of the loop aerial, or are you using two aerials?
Yeah. So the loop antenna, the reason we use a loop as opposed to a bit of a wire, long piece of wire, is that we're interested in the magnetic field, not the electric field. The magnetic field is less susceptible to the vast amount of interference that's around at these low frequencies. So it's a magnetic loop antenna, and that is sensitive in one direction and not at 90 degrees to it. So when the frame of the loop is pointing at the transmitter, then that's your maximum sensitivity. When the face of the loop is pointing at the transmitter, that's your minimum sensitivity. I have two things in life which I keep meaning to get around to, and that's one, to use two loops and drive left and right channels within Spectrum Lab and find some way of combining the results. The second, one of the reasons why these signals are weak is that it's a non-resonant antenna. So it covers all the frequencies, but that doesn't mean that it's tuned to any one frequency. I would like to experiment with something like varicap diodes to be able to, with something like a Raspberry Pi, which can handle all of this dead easy. I mean, once you've developed the application within Spectrum Lab, in the lab, as it were, there's no reason why, once you've identified what you need, that you shouldn't take that information away to something like GNU Radio or anything really, and implement a far more effective way of doing it. So I'd like to do that and see if I can use the outputs to drive a voltage onto varicap diodes, and then, or something like that, I don't know, switch capacitors in and out. And actually, because we're only making measurements every 10 seconds, you've got oodles of time to be able to tune the loop to a new frequency and make a measurement that way. So long-winded answer, sorry.
No, that's okay. That's fine.
I'm fairly new to radio astronomy. If you laid the loop flat on the ground, would that make it more omnidirectional? Because the face of the loop would be either pointing at the ground or pointing at the sky.
Yeah, I've never tried that. Yes, okay. Oh, I suspect not. Proximity of the ground. We're getting into the physics of the way the magnetic field interacts down at ground level. Aerials of whatever kind don't work very well when they're lying on the ground. One exception is that I have had meteor pings off graphs with a Yagi antenna just lying on the ground.
Yeah, I have tried that, Paul, with mine flat on the loft roof, but I find that it then picks up so much local electrical interference from all directions as to be more a problem than it solves.
Thank you. Any other questions on ionospheric disturbances before we go on to the?
There's other questions coming in on the chat which you can't see. Perhaps
no. If I go out of screen share, I can get chat, but when I'm in screen share, I can't, and I don't want to mess around too much. If there are any questions there,
you want to read them, Paul?
Yeah, Diana is asking if the output is from Spec Lab a CSV file.
Yes, you really describe the file. So it is a CSV, even though the file has a .txt suffix to it. And the reasons for that are lost in history. We might as well label the file as a .csv file. Or use a tab character when we write the conditional action script to export to a proper TXT. It's weird. I don't know why it started out that way, but so many people use it, and other files are saved that way. It's strange, but it is a CSV format, even though it's got a TXT suffix.
And Mikey is asking the question, how can you adjust for frequency errors in the sound card? I know how to calibrate a radio VFO by feeding, say, 600 Hertz heterodyne signal into the program and then adjusting the receiver VFO to make it 600 Hertz. However, that doesn't eliminate frequency error from the sound card itself.
I don't know the answer to that. It's a bit of functionality. I know there's a lot in there in the user guide and instructions on how to feed in a GPS receiver output with 1 pulse per second pulses into Spectrum Lab, but I don't know. So we would be on the same level of knowledge there.
And Alan is asking, in Capture, can you also capture audio?
Yes, actually I addressed that in the next section. So you don't actually use the capture button, but you could program one of those side buttons to hit audio and to do it automatically, or on that top script, on the top file settings. I didn't cover this, did I? There's a gray circle. Dare I go back? No, I don't dare go back. But on the top, along the menu options at the top of the screen on Spectrum Lab, we might see that in the next one. There is a gray button, and hitting that gray button starts the audio recorder. Or you can, as I'll explain in a minute, you can also do it through conditional actions. Any others?
Yeah, I think that's it from the chat.
Jolly good. Excuse me. Oh, shouldn't be doing vodka at this time of day. Right. So let's go on to our final chapter, Meteor Detection. Now here, the aim is to detect meteors through reflections off their plasma trails. So this is really plasma within a plasma, because the ionosphere itself is a plasma, but once you have a meteor burning a passage through the sky, you get a trail of thicker plasma. So you do need a radio receiver and an aerial covering the frequency of the source. People know that we use the Graves radar transmitter as the searchlight illuminating the sky, which is a very powerful source but has its problems. Okay, and the requirements here are, first of all, we need to detect a burst of reflected signal. We then need to characterize them, get a measurement for a timestamp, magnitude, the duration of the event, and Doppler shift. And then finally, capture an image of the reflection. So this is what we need Spectrum Lab to do. as usual, we'll start from the factory default screen, and we'll now set that up for, we'll now change over to the Meteor scatter.
Here's that grey button. I should have said that grey button starts the audio recorder.
Scatter application. So into File, into Load Settings From, and select the Meteor scatter configuration and open that. And we see some quite significant changes in the screen when I get rid of these unwanted windows. We've lost the spectrogram across the top, spectrograph rather, across the top, and the waterfall has been changed on its side. So instead of scrolling from top to bottom, we're now scrolling from left to right.
To left. Sorry about that.
This is the start of the new session, Meteor scatter configuration. And we have a message printed on the screen here, and that's from the Conditional Action script, and which has a line to say that at the start of each session, print out a message identifying the particular configuration that we're using at the moment. So this is all part of the metadata to sort of record the configuration of the system as we start to make observations. This all looks a mess because we're actually still looking at the microphone inputs of the laptop. So I'll go into Options over here, and I will go into Audio Input, and instead of the microphone array, I will choose the Fft dongle SDR receiver that I use for Meteor scatter work, and apply that. And sure enough, we start to see the signal from the Fft dongle. Right, I'd like to show another feature of how you can capture metadata, and that's to go into the periodic actions screen over here. And we will put that up in the corner here. And there is an option here for screen capture. So let's zoom into that and explain a bit more about what we can do with this. So here we can enter additional information about the system setup into a window that's overlaid on the top of every single screen capture. So the information that we can enter, we put into this screen. You can have up to 4 lines of information. So I've got the date at on the first line. The second line, I've got the frequency that the Fft dongle receiver is set up to, and also the center frequency for the Spectrum Lab screen. I also have the serial number of the particular Fft dongle receiver I'm using, because I've got 2. The next line is showing the configuration script file name again, so that we know all of that detail. And finally, there is a line about the antenna that I'm using for the observations. So vertical polarization, I've got 2 vertically polarized antennas. One's got a wooden frame, one's got a plastic frame. So I'm just identifying which one that I'm using for this session of observations. And if I click here, we can see how that information is captured in a box, which is, as I say, overlaid onto the top of every single screenshot. Right, so we'll close that and we'll go back to the full screen operation. Here we see the Meteor scatter application, but using the GB3 VHF beacon instead of hoping to have meteors pop up on demand, which they never do. What I wanted to just go over here was the event messages, which are appearing here. And in normal operation, there will be 1 message for every Meteor event that the system detects. And the message basically gives a serial number here, which is reset, an event number, which is reset at the start of each hour. We have the amplitude of the signal at the start of detection, the duration, which is a bit problematic with this particular signal, and a measurement of the Doppler shift. So the Doppler shift, we're showing -8 Hertz for the carrier. If we get into the tone sequence, we'll see that the Doppler shift values are going all over the place. The signal level, I'm pleased to say, is fairly static because of the mechanisms we've used for overcoming the window function. So that's working well. So that's basically the screen that you see for meteor scatter operation. Sorry, there's no meteors at the moment, but that's the best solution I got. I'm now going to talk about some of the other functions which support this operation.
Right, I'm sorry about the jerky nature of that video and the fact you completely lost the cursor that I was using to point. That was very frustrating. I did a lot of work doing videos to support this talk, and it looks quite smart on my laptop, I promise you. It was a bit of a disaster when I started to check it out with the Zoom overlaid on top of it. So apologies there. I hope the messages came across. Here's the component set up for meteor scatter. So and it's really fascinating. The cursor on my laptop is huge. It almost fills the square that I'm looking at here. And somehow it just gets translated into this little tiny, insignificant little blip, which is really difficult to follow. So apologies for that. It's not me, it's them. Right, okay, so the biggest difference here is, well, just running through it, we've introduced the preprocessor block here, which is doing our decimation function that I use in Spectrum Lab for this. But you can see that there is a new link going from the right chain into the left. And this is where the this is where the Q samples are coming up to be mixed and processed with the I samples to produce the output to drive the rest of the display. So I think that's that. Go on to the next one. We've looked at the conditional actions script in detail. Now, what I've got on my screen at the moment is those green lines just firing away like nobody's business. There's probably 3 or 4 changes per second. You're only getting a slight taste of that. Again, that's the Zoom overlay, but it shows you the way in which the conditional actions are firing away. And the nice thing about it is they're all green. If they turn red, you've got a problem. Output from the Spectrum Lab, the conditional actions produces a text file, an event log of this format. I don't think there's anything new here. Obviously, different format, the same principles apply. Recording, okay, so we record a timestamp, we record the strength, sorry, no, the amplitude of the, oh no, that's the event number. So we give each event a reference number which restarts each hour. That's the amplitude of the meteor scatter. That's the background noise. That's the maximum Doppler shift. And this is an old script because I've just got a counter here. That should be
That's, yeah, maybe use the same label. That would actually be the number of seconds. Yes, we've got it down here. This is the output of the text file. So timestamp, event number, signal, magnitude, noise, Doppler shift, and duration of the meteor. So that's what comes out of Spectrum Lab, and you can use for plotting. The second thing that comes out is a whole sequence of screen saves, 4.5 minutes in duration each. You can see the pretty eventful 4.5 minutes. I don't know if you can make out the time. Oh, no, down here. Okay. So here we have our metadata with a date of the 14th of December. Which, if you know your meteor science, you will understand why we've got such a busy screen. I actually remember that night. I went out about 2 o'clock in the morning. Well, what time is it? It's 2:22 in the morning. Got the full paraphernalia, ladies' tights. I admit to that. Pajama bottoms, jeans, a t-shirt, shirt, jumper, coat, go outside, and within 20 minutes you're freezing cold. And in that period of time, I think I saw, what, three streaks of light across the sky. I came back in and I looked at this chart, and that shows you the advantage of doing meteor detection by reflections, radio reflections. So you can now check this if you want against the event log to see if there's any interference there. And then to answer another question that came earlier, we can save audio files driven by the Conditional Action script. The nice thing about Spectrum Lab is that it's nice in this case, it's a bit of a pain elsewhere. There's a huge data buffer on the input to Spectrum Lab. But for here, it means you can capture a recording from 3 or 4 seconds before the event actually hits the detector. So you can get your audio captures of the whole event rather than being driven off the actual trigger detection time. I think, if I remember rightly, yes. So, okay, as I say, the user guide runs to just under 300 pages of information, contains a huge amount of information there. If you've got a question, if you've got a problem, look at the user guide first, because if you take the second step and the answer is in the user guide, then you're unlikely to get a response. But if it is something special, then Spectrum Lab users on Groups.io, there's usually a good, pretty much response to questions. Finally, I just have to say the amount of help, not necessarily here. Wolfgang Beuscher does monitor this and occasionally comes back to it. But as I say, he has a day job and all of this is done for free. But on 3 or 4 occasions, he has added a feature into Spectrum Lab to help me with my work. So I'm most grateful for that. And in fact, one of the features here was added specifically for this. If Wolf decides it does improve the overall functionality, he will spend time to do it. So that's very much appreciated. Thank you.
Brilliant stuff. Very good, Paul.
Well done indeed.
Paul, I have a question. Years ago when we were doing lots of this, well, I don't know whether you're still doing it, but Victoria Jackson wrote us a script to clean and unravel all these meteor pings. I wonder how that developed.
It developed into a young child. I can't remember his name now. Victoria and Chris, yes. They've relocated up to Scotland and whatever. Yes, she did a grand job doing an application which allowed you to brought up the event log and also brought up the screenshot for that particular period of time. And this was way back, 5-6 years ago. It meant I was able to just go through the event log, and with the screenshots coming up in the right place, and I was able to identify incorrect events in the log due to aircraft reflections. No, I haven't done any more of that in the last few years. Other things have got in the way, as they have with Victoria.
Is there still a reasonable interest in all this? I don't know whether these sort of new members in this group are actually doing any of this meteor ping reception.
There's a lot of there is always a steady turnover of people who do meteor detection. They sort of come in, they get involved, they develop scripts, and then they drift out. One issue that we have, and Tony, your question is so appropriate. I don't know whether someone's prompted you or not, but one issue we have with meteor detection by this way is the Graves radar system that is used to illuminate these events. Graves, because it has this beam that scans the sky, because it's a military system that we know absolutely nothing about in terms of technical characteristics other than what we can guess from what we see, really limits the amount of science that we can do here. And there is a lot of science here. There's a lot of science to do with the plasma trail, the way the plasma trail fluctuates, and what the plasma trail tells us about air pressure up there in the atmosphere. This is recombination rates and whatever. So there's a lot of science there, but it's not possible with graphs. What we are thinking about doing is implementing a purpose-built meteor beacon in the UK. We've got to the point where we've established that we probably would get the necessary authorization for it. This would be at 50 megahertz, which is far more useful for meteor scatter operation than the 144 megahertz that Graves uses. We get more, the reflections are much stronger at a third of the frequency. I think they're 9 times, it goes as the cube of the frequency, so they're 9 times stronger. So we are interested, this is RAG, this is the group. And I am going to be having a telephone conversation with the guys over in Belgium who run a similar system to see if what help they can provide in terms of advice. The issues I've got is that although there are enough people keen enough to build a beacon, we need a location for it. And I guess we will also need a steady income. The estimate is about £400 a year for the electricity to feed the darn thing. So I've got to think of a way of meeting those two requirements. And here's a plea to all of you out there for ideas, thoughts, and expressions of interest in supporting the project of this nature. So thank you, Tony, for that.
It sounds an ideal thing to put down at the radio telescopes at in Cornwall. Sure, they could afford a bit of electricity to put up a 50 megs beacon.
Paul,
that's one possibility.
Paul, from your last comment, how does Hereford sound as a location?
Well, one of the questions I'm going to be asking the Brams people, those are the Belgian team, is the location, or the best location for something like this. Aircraft reflections are a real issue with the operation over in Belgium. And if there's a location that is the proximity of an airport might be relevant. So I don't know the answer to that.
I'll just provide a little bit of information to why I asked the question. BT have a big satellite station southwest of Hereford called Madley. It's in a geographical depression. It was a World War II airport, well, landing site for planes. Now then, BT owned the site, but many years ago they reduced their acreage and sold off land. A portion of land adjacent to BT Madley is Madley Environmental Centre. And we celebrated the 50 years anniversary of the moon landings there. So there is potential within that piece of space, and it gets its security from BT Madley.
Okay.
Put that at the back of your noddle, and if it's of use, I can pursue.
Okay, thank you, Norman. I think the whole subject could do with a separate discussion. At this point, if people could mail myself or Paul Hearn, or both of us, with expressions of interest and ideas, that would be extremely welcome. So let's just have other questions related to the presentation for now, but that's a plea for help.
Okay.
On the subject of Spectrum Lab, Paul, have you, I mean, all the things you've covered, the stuff he's done, I mean, it is absolutely staggering how configurable it all is. So everybody's using it in different ways. Have you any idea how many lines of code there are involved in what he's written? I mean, it seems incredible to me.
As I say, it's a labour of love, and it's been developed over the years. No, I've absolutely no idea. I just understand how popular Wolf is.
Yeah.
So if there are no more questions, right.
I'm using Spectrum Lab with Windows. I've found that I keep getting lots of problems every time I get a Windows update.
I think those are absolutely nothing compared to the problems Wolf had when Vista came along, or Windows 7, and the entire sort of philosophy of files and whatever changed. So that's again, you know, I'm grateful that he updates things and keeps it going.
I have to say, now you've said that people have run it under Wine, I might have a go on my RPI 400 with an external sound card, because I've got Wine to try and run various things. It'd be interesting to know how well the Raspberry Pi would manage, because it'd be quite nice as a low power device to sort of lock it away to do these sort of things permanently.
Yes, and I think the philosophy is sort of using Spectrum Lab to do the investigation and whatever, and then using things like GNU Radio to perhaps implement something more effective and efficient. I think that's one particular approach.
Interesting. Norman, can I ask you a question?
Sure.
You live quite close to Dr. David down your way. He did a lot of work on this and looking at what the what the the plasma balls were doing. Haven't heard from him recently. Is he still alive and well? Oh, you need sound on, Norman.
Yes, it helps to press the right buttons. I was talking to David a couple of weeks ago, and we're both looking forward to less lockdown restrictions. There's a complication for David in that his mother-in-law is not very well. So Margaret is spending a lot of time in Cornwall.
All right.
But David's bright and cheerful. In fact, I hope to invite them both up for lunch one afternoon and go for a wander locally.
Brilliant. Thanks, Norman.
So another aspect is we're developing, wearing another hat, a H-line signal source. And we'll be taking David's offered his benefit of his experience and equipment to examine our prototype. Okay.
All right. I think I think I demonstrated an H-line signal source at the Space Center once, which was the sort of X harmonic of my SI 570 programmable oscillator. I could put it one side, you know, some room a long way away, and we could pick it up because it was quite powerful.
Yes, it's illegal transmitting, Tony.
Yeah, that's right.
Paul, Hyde, I'll do a quick summary of what I said earlier in an email to you.
Thanks very much, Norman. That'll be appreciated.
Paul, can you hear me okay?
Hello, Ian.
Hi, Paul.
Hi, Ian.
Great presentation, Paul. Just a quick question. When you showed on your components diagram, how did you link the filters to the two channels? You showed a line between the filter and the box below. Could you just sort of guide us through that one?
It just happens.
All
you
right.
tell the filter that you've got IQ input, and the line magically appears.
Okay. Thank you.
Hey, Paul. I'm a volunteer at the planetarium at Teesside, and what it is they're looking at getting a thing from the SuperSID project at which is based at Stanford in America, and they basically built a small receiver that they're selling at a reasonable price to different organizations and educational organizations. They're looking at getting something like that. I was wondering whether there was anything like that that's produced in this country.
I know that UKRAA do VLF receivers for this application. The big difference is that with the VLF, with the UKRAA application, the receivers are frequency specific. So they produce very much better quality outputs, but you do need a separate receiver and a separate loop antenna for each frequency. Whereas the SuperSID, I do know of that. That's pretty much a souped up version of what I've been describing here.
Hey, Paul, can you stop screen sharing so we can see everybody better?
Oh, I'm sorry. I should have shouted earlier. Where are we?
You'll be able to see the chat then as well.
Yeah. That's really stupid of me. And where we stop share.
There you go.
My apologies, people. I can see the chat.
Well,
okay.
gentlemen, I'm going to wish you all good day and retire. I'm getting hungry.
Cheers, Norman.
Bye, Norman.
Bye.
Bye, Norman.
I was going to say, just on a slightly different subject, Paul Hearn. I mean, I think I posted on the RAG group the stuff that our friends in Germany posted on things you can do for the H-line reception. Absolutely fantastic! All that stuff about the various aerials, antennas. I want to build a dipole and a CD just pointed at the sky. I mean, absolutely amazing what they were doing.
It was extraordinary. That was a very useful link, I have to say.
Yeah. I mean, real gives you inspiration to just have a go, doesn't it? That you can use such simple things.
Yeah. Are there any more questions for Paul Hyde on Spectrum Lab? Otherwise, we can formally close this session and I'll stop the recording. Any more for any more?
Only is he going to post his setup details?
Yeah, absolutely. I don't know what the best mechanism is. I can just post an email on the groups IO with both of the config files attached to it.
Brilliant.
Yeah, that would be very helpful, Paul. I'd like to conclude this by saying thank you very much. The effort you've put in over the last few weeks have paid off handsomely. Your videos hung together. That worked. Maybe the cursor didn't, but the video and audio was, was good. So thank you so much, Paul. Thank you very much.
Yeah, well done, Paul.
Thanks, Paul. Thank you.